Okay, let's do that. All right. Hello, everyone. Thanks for joining us. This is a tech webinar hosted by KIAT-Georgia Tech Semiconductor Electronics Center. I'm Dr. Hong Young. I'm the center director at Georgia Tech, and this is my great pleasure to have one of my colleagues here at Tech, Professor Nian Liu. As you see from the title. He will share his research regarding materials, devices, and systems, and they are related to electrochemical energy storage. Before jumping into his talk, let me briefly introduce him. Currently, Dr. Liu is an associate professor at School of Chemical and Biomolecular Engineering here at Georgia Tech, and his research has been broadly interested in the combination of materials, electrochemistry, and microscopy for studying the global energy challenges. And specifically, his lab is focusing on electric vehicle battery and stationary battery science and technology. With that, today he will share his ongoing research. So please welcome Dr. Liu.
Hey, yeah, thanks, Hong, for the introduction and the opportunity to speak in this webinar. Um, and so my research area is electrochemical energy storage. And I work with KIAT on a flow battery project, which I will talk towards the end. But I will also give you a general introduction of all the energy storage research going on in our lab. Okay, so this is what I usually do when I talk with international audience, which is the brief introduction of Georgia Tech. It is located in Atlanta, which is in the southeast of United States. We have a direct flight to South Korea, and the Georgia Tech is very famous for the engineering, and so we're ranked number 4 nationwide on that. So you may ask, what is famous about Atlanta? Apart from Georgia Tech, we're also famous for the Coca-Cola, which is introduced more than 100 years ago in Atlanta, and its headquarters is also in Atlanta. So about energy storage, I want to start with a little bit of history. So it actually, lithium-ion batteries started about 30, 40 years ago. And the first market was in portable electronics, such as cell phone and laptop. So in this picture, this is the latest model of phone. And this lithium-ion battery has been very successful in being adopted as the battery for these devices. And in the past decade or two, lithium-ion battery expanded the market from the electronics to electric vehicle, as you can see in the picture here. So it is actually a big transition because typically car use internal combustion engine and gasoline to power. But the electric vehicle use batteries. And the battery technology went through a new birth from the mobile phone to EV application. Through that process, a lot of new innovation took place to make this successful. As for now, in the US, about 10 to 20% of the new vehicles sold every year are electric vehicle. And this is becoming more and more popular and common to see electric vehicle on the road. And but unfortunately, a few weeks ago, the EV tax credit ended for US. And for the future, how will the sales of EV go is actually quite uncertain. So we'll see how it goes. But for us, we always look for new market and new application of electrochemical energy storage. And so I'm going to tell you what I think is the future, and that's the data center. When you use ChatGPT, for example, or other AI tools, you actually activate a lot of background actions, including the storage, information storage, and processing, and computing. So these things take place in data centers. Nowadays, there are more than 4,000 data centers across United States. And South Korea also has a lot, close to 100. And these data center, you don't actually go to data center to do the computing, but there are a lot of them doing the service for us in the background. So in the data center, they have to run 24/7, and they can't leave electric power for just even a second. So that's why you need to have a very robust backup power in case the electricity there's a power outage. So let's do some simple calculation. The 4,000 data center in the US, in total, they consume about 30 gigawatt of power. And if you have a power outage, it takes about 10 seconds for the diesel generator to kick in. This diesel generator can provide a backup power, but it need time to activate. So in that 10-second gap is when you need a short-term but very quick responsive energy storage backup device. And this is called a UPS, uninterruptible power supply. And usually batteries are the best, most suitable device to serve this function. And to supply 30 gigawatt for 10 seconds, you need about 100 megawatt hour batteries. And that's compared to electric vehicle, that's not much bigger, but it is already a very large amount of energy and a lot of batteries. And also, these kind of batteries, you probably don't need to cycle them as much as the electric vehicle battery. Like every day you use it. But these battery, they only use maybe once every 3 months or a year, right? But they have to be there and they have to kick in when they're needed. Because the value of what they protect is so much higher than a vehicle, these kind of battery can be sold at a much higher price. So these batteries are very unique, and they have different criteria than the EV battery. And that's why I think that's an opportunity for researchers to work on them and develop them to be readily available for use in data centers. So, what kind of battery is good for this application? In my opinion, the aqueous batteries are very promising. If we compare aqueous battery with lithium-ion batteries, they have different electrolyte. Lithium-ion battery have a flammable organic electrolyte, and actually most of the fire comes from these kind of intrinsic flammability. And aqueous battery, in contrast, they use water-based, non-flammable electrolyte. So it's much harder to catch fire and much safer for use, especially inside a building and in other safety sensitive applications. And the cost, supply chain, and scalability may also have advantage over lithium-ion batteries. So just to show you, I think you probably know this accident, which happened a few weeks ago in Korea. And this building hosts the data center and also the backup power from lithium-ion battery, which is flammable. And when the lithium-ion battery catch fire, the building has a fire. And this caused the interruption of the government website and service center. So that caused a lot of chaos. And if we can use a non-flammable battery, then you can potentially avoid this kind of accidents. And just to reiterate, these aqueous battery may not replace all the lithium-ion battery. The EV can still use lithium-ion, but for certain specific safety-sensitive applications, aqueous battery may become a promising alternative. So there are a lot of challenges for aqueous batteries. Actually, aqueous battery was the first battery people ever invented about 200 years ago. They were used even before lithium-ion. But lithium-ion has certain unique advantages, such as energy density and also the lightweight. That makes them very promising for the portable electronics and electric vehicle. So aqueous battery has practically lower energy density, and that is limited by the water stability window, which is smaller than the organic electrolyte. And also the electrolyte, they tend to change in composition in charge and discharge due to the involvement of water in the reaction. That's another challenge. And finally, the cycling stability in water-based electrolyte is usually lower due to the side reactions like dissolution and dendrite formation and water decomposition. So these are the practical challenges. But theoretically, if you look at the energy density of aqueous chemistries in this table, this zinc chemistry actually theoretically can uh, uh, have similar energy density as lithium ion. Some of the chemistry even have higher numbers. But in practice, lithium ion can utilize 90% or higher of the theoretical energy, but these zinc chemistry only utilize 10% or so. So that's why in reality they have lower energy. But if you can increase the utilization of these uh, chemistry to higher, then you have energy density that's similar to lithium ion. And that's what we are trying to do. So later in the talk, I will also briefly show these two chemistry, nickel metal hydride and zinc iodide. And they also have very promising theoretical energy. Okay, so in the first part, I will talk about a rechargeable aqueous zinc battery. And then in the second part, I will talk about the device level engineering to enable the microtubular flow battery. And I will also later introduce the background of why we work on that. And then finally, I will talk about a project that we work under the sponsorship of KIAT. Okay, so let's talk about zinc first. Um, so zinc has been commercialized for decades, and they're commonly used in the hearing aid device. And these batteries are very small, has a lot of energy, and it's very safe. So you can put near your head without worrying about catching fire or explosion. And but the problem is it's a primary battery, so you can discharge a lot of capacity, but you can't put the charge back. And later cycling, you get virtually zero capacity. And we analyze this problem, and we think the first root cause for this is the zinc oxide passivation. So as you can see in this image, we fully discharge the zinc and then open the battery and do a cross-section image. You can see the surface of the zinc is covered by a zinc oxide passivation layer. And the inside is you still have a lot of fresh metallic zinc unreacted, but they can't react further because the surface zinc oxide prevent electrolyte from reaching the zinc in the middle and then stop the further reaction. Um, so that's actually the root cause, one of the root cause for the uh, zinc oxide, for the irreversibility of zinc. And that, but that also give us a hypothesis. If we can reduce the feature size of zinc to below this critical passivation thickness, then we can fully convert the zinc to zinc oxide and then back to zinc without the passivation because you will fully convert before this thickness of zinc oxide is built. And that's the first hypothesis. And then the second root cause of the problem of zinc anode is the zincate dissolution. So during the conversion between zinc oxide and zinc, the zinc species will go through a zincate ion, as shown in red color. And this zincate ion is soluble. It doesn't have a lot of solubility, but its solubility is enough for the species to move around, and the shape of electrode will change over cycling. And that even though you start with nice shape in the beginning, it will aggregate and grow at places you don't want after cycling. And that is the secondary root cause of zinc electrode. And we also have a hypothesis to address this problem. The hypothesis is to encapsulate zinc um, inside a confinement structure so you can slow down the escape of zincate. So with these two root causes and that their hypothesis to address them, we design this kind of structure. So this is a zinc oxide nanoparticle. So it's small size, less than the critical passivation thickness. And then outside we have a carbon coating. And this carbon coating will encapsulate the zincate species and slow down their dissolution. So we have the two approaches in this design to address the two root causes. Historically, zinc electrode, people don't use this type of structure. And, our approach is very innovative. And we hope to use this kind of material innovation to address the historic problem of zinc electrode. And these are the carbon coating has a pore in it. Why we need a pore? Because we want to block the zincate, but we still want to allow the hydroxide ion to come in and out, because you need that for the reaction to take place. And this is how the material look like after synthesis. And you can see the zinc oxide in the middle and the carbon outside. And then we did the pore size analysis on the carbon, and we find the pore size is indeed between the hydrated ion size of these two ions. So we throw the particle in the KOH electrolyte and to see if indeed the coating can confine the dissolution, slow down the dissolution of zinc oxide inside. We measure the concentration of zinc in the liquid solution, and we find that with the carbon coating, the zinc dissolved is much less than the bare zinc oxide particle. And we further assemble these particles into a secondary particle to further suppress the dissolution, because now in the middle you have some zincate. It will be very hard for them to go across so many layers all the way to the electrolyte outside. So if you compare these amount that's dissolved from these particles, this is better than this. And then this secondary particle is even less than the primary core shell particle. So we use a very complicated method to synthesize this initially. And then we work with a company, GP Battery, to develop a much more scalable and simpler way to synthesize the same structure. And this is spray drying process, and we can produce 100 gram at a time. In the past, we can only do 100 milligram. So with this large scalable approach, now we can further look into the commercialization. And that's what the company has been doing. So, this solution is not the only, not the only problem, or it's not only found in the zinc electrode. It is also pretty common in other aqueous battery chemistry. For example, nickel metal hydride. And this AB5 uh, material is the anode material of nickel metal hydride battery. And it has mainly the rare earth uh, and also the nickel, but it also has some other metal elements inside. It's alloy. So this material is very good at extremely low temperature, -40 degrees C. But it has a dissolution problem. So if you cycle it for many times, the metal inside will come out of the particle, and then that will degrade the performance of the material. So what we did is design and made a coating specifically for this AB5 particle. This coating here is lanthanum fluoride. We chose that because it's stable in the electrolyte, and also it has a similar structure, composition as, the lanthanum is the same inside the particle and in the coating. So it has good adhesion, uh, and you can also make it very uniform and thin. So after coating lanthanum fluoride, we tested the solubility again, similar to the zinc. And you can see that with the coating, the amount of nickel, lanthanum, cerium that's dissolved into the electrolyte is much suppressed. So that indicate the function of the coating is indeed working. And with the coating, you may think, right, will that make the low temperature performance worse because it may slow down the ion transport and block the ions to react with the particle, right? So we did the low temperature discharge capability testing. First, I want to show you this picture. At -40 degrees C, if you have high concentration of KOH in water, the solution can maintain its liquid state, right? And you turn this vials over and the liquid come down. These lower concentration of KOH all freeze, but the high concentration one can maintain its liquid state. And then we did the discharge at this low temperature in this liquid electrolyte. The black one is the pristine uncoated AB5. And if we coat them properly, you can deliver the same capacity at -40 C. So the coating actually didn't make this performance worse. And it prevented the dissolution. So that's very good. But if you use a different type of coating, then you can actually indeed make the capacity lower at low temperature. Okay, so -40 is a very extreme temperature because typical lithium ion cannot discharge below -20 C. So this is a big success from the nickel metal hydride. So back to the zinc. So far, the approach we use to deal with the dissolution is to passively encapsulate. However, over weeks or months or years, the zincate will still slowly escape out. Then for those zincate that's escaped, is there any way we can bring them back into the particle? Right? That's the active management. And we try to achieve that. But let me show you this video first to give you an idea, how does the zinc deposition look like if you don't have any confinement. So you can see this is zinc deposition on carbon fiber paper electrode and forms this dendritic structure instead of uniform flat film. And then when you switch the current to strip the zinc, they will peel off and then form dead zinc, which cause the efficiency loss of the electrode. So what we did here is to spread a layer of silver nanoparticle on this carbon substrate. And then silver can alloy with zinc. And then we hope it can anchor where the zinc deposit and then change the deposition behavior. You can see now with the silver, the deposition is much more uniform. There is no dendritic structure. And when you switch the current to stripping, it also uniformly disappear. And there is no dead zinc and very uniform. So silver can actually spatially control where the zinc deposit. And here is the reason for that. If you just have the carbon, then zinc deposition has to cross a nucleation barrier. But if you have silver, because it can alloy with zinc, the barrier is much lower. And then, so if you have silver and a carbon both existing, then the zinc will prefer to deposit on the silver first. That's how silver can spatially control where the zinc set deposit. And it forms a anchor and always bring zinc back to its nearby place. And you can actually control spatially where the zinc deposit. And we did the X-ray diffraction at different state of charge to confirm that you can form this, you can detect this zinc silver alloy after the zinc deposition. And then after these silver are saturated with zinc, then metallic zinc will further form on top of that. So this confirms the mechanism. And after we learned this principles of the alloying mechanism, we actually applied it back to the particle structure that you have seen earlier. The difference here is we place the silver nanoparticles on the inner surface of the carbon shell. So even though zinc over time slowly escape out, because the silver is inside the particle, the escaped zinc will prefer to come back and deposit inside the carbon shell. So that actually actively bring them back, even though over time they slowly escape. That's the design here. And we can make a lot of particle and you can see them under the TEM. Uh, this is the zinc oxide, and then this silver nanoparticle, and the carbon is on the most outside. Right? You can see, higher magnification image, the carbon outside, silver, and the zinc oxide. And we tested the battery performance. So the red one is the structure that you just saw, and the blue one is the zinc oxide carbon core shell structure. There is no silver, so they uh, are better than the zinc oxide particle. They last longer, but still they decay around the 50 cycles. And the one has the silver last longer than both the black one and the blue. So this shows the success of this kind of design. And then we also did the elemental mapping to confirm this works in the way we design um, through the mechanism that we design. So this is before cycling. And you can see here, this image has the zinc inside, silver in the middle, and carbon outside. And after charging, you can still see the silver particle, and the zinc is the blue color. And then you can see they are surrounding the silver. Right? This after charging, zinc oxide become metallic zinc, and then this metallic zinc deposit next to the silver. And the red color is the carbon, and it's nicely coat everything. So there's no zinc growth outside of the carbon, um, indicating this structure can well confine everything inside and achieve stable morphology over many cycles. And then this kind of material is also able to discharge at negative 40 degrees C. I'll skip this thing and then talk about the microtubular flow battery. So the motivation for flow battery is indeed the long duration energy storage. So this is Texas energy consumption and the renewable energy generation over a year. And then this is year 2021. If you remember, in that February, Texas had a power crisis, and people have a blackout for extended period of time. And that's because the temperature is very low, energy consumption go up, and over that period of time, there's very little solar and very little wind. And that, makes the production not able to meet the demand. So that's why we need a energy storage capacity over multiple days, not just one day. You need multiple days to enable you to have sufficient energy to go over these kind of extreme weather to make the grid more reliable. And in order to have multiple days of capacity, you have two choices. One is a traditional battery, um, which cost a scale with the capacity. And the other kind of battery is the flow battery. It's very unique in the sense that it has decoupled power and energy. So the orange component is the power module, and the blue component is the tank for the electrolyte. If you just need to have a more capacity without more power, you don't need more power, you just need more capacity. You can simply enlarge the tank size, and the tank is cheaper than the power module. So initially, if you have a small battery, the cost may be higher than 8 type. But as you enlarge the capacity, your slope is lower. So for a large scale battery, the flow battery can have lower cost than the lithium ion and other type of coupled power and energy. So what we innovate is making the power module lower cost in the flow battery, because the power module is taking up a large fraction of the cost. And we reduce the size and the cost of this module to make this flow battery system more cost effective. And the way we achieve that is to use a microtubular configuration. So the membrane is in a tubular shape, and you have electrode inside the membrane and another electrode outside. And the electrolyte one flows through the inner of the membrane tube, and the electrolyte two flows through the outer volume. So they don't mix, and this is how flow battery work in a microtubular configuration. And this has certain advantage over the conventional planar um, cell. The distance between electrodes smaller, and the membrane surface area is larger in a given volume. So you can shrink the volume of the device and achieve the same power. And also it's very scalable. This is how the device look like during operation. The two pumps circulate the electrolyte through them, and then these are the two terminals for the two electrodes. And you can see the membrane is about half a millimeter in diameter. And we have carbon fiber electrode inside and a zinc wire outside. And this device is very compact, and it is scalable. You can make a bundle of a lot of these membrane tubes and a lot of electrodes inside and outside. So we achieved a very high volumetric current. So the volumetric current density of our microtubular cell, shown in red, uh, is much higher than the planar configuration at the same cell voltage. Right? The red one is about 5 to 10 times higher. And this is due to the unique configuration and geometry. And we did some simulation to figure out the different scenario, like conductivity of the electrode is important for this device to be very long, because the electron has to deliver this way, right? It's different from the planar configuration. And also the uh, conductivity of the two electrodes has to be symmetric. If one is more conductive than the other, then the reaction will concentrate on one side. And also we study the mass transport in addition to the electron transport. And we find that you need a uh, high velocity inside the tubular space for the efficient mixing and also better performance. So we also studied the arrangement of electrodes inside of the device. You can do this kind of coaxial arrangement or the non-coaxial. And the coaxial one will give you lower internal resistance But non-coaxial one like this is easier to make. So you have it's a trade-off between these two things. Okay, so after talking about the microtubular flow battery, I will finally talk about the KIAT-sponsored project, which is about a pumpless flow battery. So in flow battery, like I said earlier, you need a pump. Um, and this pump actually circulate liquid electrolyte from the tank to the cell to react and then bring them back to the tank. But pump also consume energy. And the more energy you consume, the lower the round trip energy efficiency of the flow battery is. So if you want the battery to be pumpless, then you want to circulate for as many as less time as possible. You don't want to circulate the electrolyte too fast, right? As slow as possible. And eventually, right, you can use gravity to slowly flow this electrolyte. So that reduce the energy consumed in the circulation. So, but people usually in the literature use very high flow rate, more than 50 milliliter per minute. And they circulate the electrolyte for hundreds of times in each charge or discharge. And because these paper, they don't care about the pump energy consumption, which is important for practical application. So we actually focus on this and the benchmark, and then try to figure out what's the minimum number of passes you need to make this flow battery still work. So this is the some results. We're organizing these results and try to submit the paper soon. But I will give you a little bit of taste of the results. So what we did is to do a polarization experiment to figure out, what's the current you can apply at different flow rate, right? We reduce flow rate from 50 to 15, and then to even lower than that, down to even 0.16 milliliter per minute. This is extremely low. And then at each flow rate, we measure a polarization curve and then determine the critical current density, and then use that current density for the future measurement of the single pass conversion. And then these are the single pass conversion we measured. And you can see at lower flow rate, your utilization or conversion is higher from a single pass. That makes sense, right? Because you flow the electrolyte slower, and then more of that electrolyte will convert. And then that's actually the first time this number is measured in the literature. And because people usually don't care about this single pass conversion. And then this is using vanadium chemistry. So vanadium has different colors, so we're able to use the change of color to measure how much vanadium reacted. And then um, so that is the main finding of this paper. And we also demonstrate here that even you flow it at a very low rate down to 0.16 milliliter per minute, you can still cycle it. And when you cycle it this way, uh, your number of pass can be even lower than 10 passes in each charge discharge. Remember, people do hundreds of passes in the literature, and we are able to reduce it to less than 10 passes. And that significantly save the pump energy. And then we can even work towards a pumpless configuration. And we indeed designed the pumpless battery, and we are using gravity to let the electrolyte flow through the cell and react, and then we have certain valve to make them really slowly flow, so we can achieve a higher utilization per flow. And we are also designing the flow channel, engineering the flow channel to further make it more efficient. Um, and then these are some simulation, and we're doing these research at the moment for this KIAT project. Okay, so I would like to acknowledge KIAT for the funding and also some other funding sources for other projects. And then this is the group members who did the work. Some of the work are shown here, some are not, but this is our entire group. I will thank all the students for the hard work. And yeah, here's the end for my talk, and I can answer some questions from the audience if there's any question. Yeah, thanks.
Thank you. Thank you, Nian. Thanks for your great talk.
Thank you.
Now the floor is open uh, so that audience can ask questions if they have directly, or you can write down your questions or comments in the chat, and I'm gonna read it for you. Any questions from the audience?
Yeah, I think this is just to show what we did, and I'm happy to discuss any future collaboration, and feel free to contact me. You can find my email from Georgia Tech website, yeah, or by asking Dr. Yao. Yeah.
So let me have a
Yes,
question.
go ahead.
Yeah, so Dr. Liu, thanks for the great talk. And I was wondering how often are the reactants replaced in the liquid flow batteries, and what performance target define their usability lifetime?
Yeah, so the flow battery, the electrolyte over time they will degrade, and some are regeneratable, like vanadium. You can do a rebalancing. Basically, you mix the two tanks together, so they will, reach the same oxidation state, and then you charge one side and discharge the other side to remake the catholyte and anolyte, and that will be enough to regenerate them. And both for some other flow battery chemistry, for example, the organic one or the iron one that don't have the same species on the two sides, then you can't do this kind of regeneration. You have to go through more steps to regenerate them. But the life of these electrolyte, typically vanadium, you can do like maybe every year, you regenerate it once, and then the system can last 10 years, 20 years. And But the other systems, it's highly dependent on the chemistry and also the membrane and other things. How fast do you have the crossover? So these kind of things will all determine how often you do the regeneration. But the target is like you regenerate it once a year or something like that.
Yeah. Thank you.
Good. Any questions from the attendees? If not, please share Dr. Liu's website, email, things like that, so that they can follow up. I don't know, my chat option doesn't allow me to do so. But other than that, again, all the attendees, thanks for coming, joining us today. And it's recorded and it's going to be uploaded to our center website. So if you are interested in sharing this with your colleagues or your collaborators, feel free to do so. Other than that, if you have any questions about this research, please directly contact Dr. Liu. Or in general, if you have any questions about this KIAT-Georgia Tech Center program, then stop by our website. You could Google our center name or you can email me. All right. Other than that, thank you again, Professor Liu, for your time and sharing your research. And thank you everyone for joining us. Thank you very much.
Thank
Thank
you.
you.
Bye.